Okay, it's 3 o'clock. I'll get started, okay? So basically, we are on the graph theory. And graph theory, you start to learn about what is graph. So you know about the vertex and edges. That's the first step, knowing about what's graph. Second one, we know about the adjacent matrix to represent graph. And then adjacent list to represent the graph. Third one, we learn depth first searching and breadth first searching. When you have a graph, how you search through the different nodes, do traversal on a node. Fourth, we start to analyze the graph. So looking at the shortest path, knowing about how you actually go through the whole graph to connect the shortest path. Or you actually working on the so-called minimum spanning tree. So it's an analysis of the graph. That's the fourth topic, shortest path and minimum spanning tree. So today we actually open a new topic that's called connected component. So in the graph, we want to analyze the connected component, okay? So connected component is another topic. Hi, Helen, how are you?
Good, how are you?
So basically, we learn how to draw a graph, that's the first, and then the data structure like adjacent matrix and adjacent list. Then we talk about depth first searching and breadth first searching to visit every node. The next one is talking about analysis of the graph. So these are the procedure when you study the graph. These are the steps that you go into the graph algorithms. So today we are going to talk about the components, connected components. So connected component, if you look at right here in USACO gateway, they talk about the connectedness. So undirected graph is actually said to be connected. If there is a path from every vertex to every other vertex, this is called connected. If there are some breakpoint, then it's actually unconnected. So basically, if there is no path going from a certain node to a certain node, so fully connected means that every node you started from there, you should be able to go to any other node in the graph. If there exists a graph, a node, from one node to the other node, there's no path going there, then we say that this graph is not connected. Okay, and the connected component, sometimes you talk about the connected component is that this is a connected component, this one connected component, okay? These are related. And this kind of analysis is sometimes related to, let's see, if you play the chess. So you play chess, sometimes you want to see if my stones, black stones are connected or not. Okay. And then, for example, these white stones, they are not connected because they don't have a path from here to here that actually with the different nodes that are connected each other. So that's not connected. So connectedness and strongly connected components. This is one topic that usually when you do analysis on graph, you will see that. Okay, so a component is a vertex or maximum subset of the vertex. That each vertex is reachable from the other. So basically the so-called component is a set of the sub-graph that each node can be connected to the other node. Okay, at least one path can go from one node to the other. That's called a connect. So connected component is a so-called class. So that means that you go into one point, all of the other can be visited by the other node. But if you drop to some other node that's not in the group, then you will not be able to visit that group. Okay, so some problem is like that. So before we go into the problem solving, we need to study this kind of the shortest path, minimum spanning tree and connectedness, and also strongly connected components. Okay, these are the something that we strongly connected components. Okay, these are the topic that we will actually see. So today we focus on connectedness and strongly connected components. Okay, that's the algorithm we are going to look at. And after that, we are actually going to finish the whole graphic part. Graphic part doesn't have too much topic left anymore. So this is what we will do today. And we will look into some other problem. Then we will start to go into the user code to look at the user code problems listed right here in the section 2. Okay, the bronze to silver to gold is division. Okay, so let's look at the strongly connected component in here. So the strongly connected component basically is talking about a graph that you actually have. You can go from one node to the other, then we call it is a strongly connected component. Okay, right here is directed map, but if it's undirected, then one way connection is not enough because the other way cannot go back. So if it is directional graph, then you must have one way to go here and the other way can go back. Okay. Otherwise, it's not considered to be the strongly connected. You need to have one way to go from A to B, the other way from B to A. Then we say these two nodes are strongly connected. Okay. If there's only one way, go one way this way or one way this way, then this one is a separate connected component. This one. Okay. So that's a concept. So basically, depth first searching of a certain graph, if you are strongly connected, then you go from this node. Basically, you should be able to search for every node. So basically, it is okay that if you have a graph, say you have A, B, C, D, okay, you have a graph. Let's assume you have a graph like this. And then you have E, F node right here. So how to find your strongly connected component? So if I started to search my graph starting from A, then I would do depth first searching. After depth first searching, because it's strongly connected, so I basically will visit every node in here. Then I can build up a set of the node that are strongly component, that's A, B, C, D. Then B, I go there, it already been visited, so I don't need that. C, I go there, already been visited, I don't go there. D, I actually go there, it's already been visited, so I don't need to go there. E, I go there, depth first searching, I will get E and F visited. So that's a state, this is actually another state, strongly connected component. After that, F already visited. So you actually have two groups of the strongly connected component. So that algorithm using the depth first searching should be able to find all of your strongly connected component. Is that okay?
Yeah.
Okay. And then this part is just like that. Okay. This chapter there's no algorithm. Let's look at something else. Okay. Let's look at the Google. Let's go strongly. There's no code, so that's there's no. So let's look at this one. Let's look at this one called programming for strongly connected component. Okay, let's look at this one. So strongly connected is actually a portion of the graph, directed graph, which there is a perfect path from each node to the other node. Okay, so right here, this one you do depth first searching. This one is only one way here, so actually you have a group right here, you have another group right here, okay? Okay, this is a theoretic graph. So to find this kind of the strongly connected component, the answer is like that, okay? You have three, there's only one-way bridge here and one-way bridge here. So this node is isolated from the other. These two parts are separated, okay? Others, you would have a circle. You would have a circle, then actually there is a two-way from one node to the other, okay? If it is a directed graph. Then there's an algorithm called Kosaraju algorithm. It's based on depth-first searching algorithm, okay? That can perform the algorithm for it. So it actually three steps involved. First, perform depth-first searching on a graph. Say let's actually do starting from vertex 0. You do depth-first searching, so you will actually see 0, 1, 2, this 0, 1, 2, 3, okay, and then you go one by one, okay, and your 3 actually no longer is pushed into the stack. Okay, you do breadth-first searching. I'm sorry, you do depth-first searching. Okay. So you visit the vertex, mark the visited vertex as done. If the vertex lead to already visited the node, push it to the stack. So you do go depth-first searching, you look for one go for two go for 3, and 3 actually can only go to 0. So this one already in there. So you push your 3 into the stack. Okay, that's actually the step 1. Okay, step 2, go to the vertex, previous vertex 2, visited the child vertex. You will have a 4, 5, 6, you do depth-first searching, and then you go to 7. 7 have nowhere to go, so you push 7 to the step as well. Okay, that's the second pass, because you go to 3, and 3 you return, you go to 4, that's another child for 2, so you actually go to here, okay? Okay, that's the depth-first searching. And then after you are done, you actually say right here, your 4 has another one. Actually, your let's see, your 5 right here, you also have a child. You could go 4 that will go to 4, so that actually already be visited. So you also push your 6 into there. These are the stack you have got stack. And then finally, once you actually have everything stacked, you will have something like this, okay? So something like this, actually, you do reverse graph. So it's a 0, 1, 2, 4, 3. Okay, this is your reverse of this graph. So actually, you perform the depth-first search on your reverse graph. Doing the similar way, you also have the visited node and the step. Okay, you pop out 4, pop out 2, 0, and then you actually have the remaining stack like that. Okay, and then you have strongly connected component based on the visited node by your 0. That's your strongly connected component when you pop out your 0 from here. Okay, then you get your first strongly related component. And then you actually pop out your bool, and then you will find your strongly connected component is 4, 5, 6 in your strongly connected. That's the second group that you have. And the last one, you pop out your pop 4, 5 out. Okay, 4, 5 out, and then you pop out your 7. And then your 7, you can only find one strongly component, related component. That's actually 7. So this one will show you the graph of the how the strongly kinetic component is called this Kosaraju algorithm. So Kosaraju algorithm is used for the strongly kinetic component. Okay. Okay, let's actually copy the code and run it. So this one in the textbook, we don't have code, so I'll use this one from here, okay? So this one is called L13, lecture 13, strongly kinetic component. Okay. And this one is called the Cora. I'm sorry. I'm not good at spelling. It's called Kosaraju. Kosaraju. Okay, Kosaraju algorithm. Okay, let's see. Something wrong. Let me get out, okay? Let me get out and open it one more time. So this part of graph, first you need to understand the definition for the graph. Then you actually know how to build a data structure, okay? And then the next one, you actually learn how to do coding with it to find the different components or show this class, those kind of things, okay? So right here, this one, you have a graph. You have integer number of vertex, and then you have a list of the vertex. List of the integer. And then you have depth first search function, okay? And you have a field order. And then you have a graph at edge and print the strongest kinetic component. And you have a transpose function, okay? Transpose function. Okay, so when you start your graph, you will actually create a graph with V number of a vector vertex. Okay, and then you can add different edges there, source and destination, okay? And then your depth first searching would have a current node, and then the VDT, the number of the vectors, vertex, okay? That's what you have. Now you actually, the constructor is right here, okay? Constructor, you will create a new list integer. So this one is adjacent matrix, okay, adjacent matrix of B size. So this one, it actually is a pointer to a list of integer type. So it actually is a pointer to an array of list of pointers. So this array of list of pointer become its adjacent map. Okay, adjacent map. So basically, your node number one would have a few different friends. Node number two would have a few different friends. Friends are where node one can go to. Okay, so this is a directed graph. You actually represent your directed graph using the so-called adjacent list format, okay, and performing depth first searching. So let's look at the depth first searching algorithm. So you have a node and then the visited node. So you call current node being visited and you print it. And then you have an iterator to go through all of its neighbors. If the neighbors have not been visited, then you will visit that. That's all thing that you will do for direct depth first searching. Okay, so after the depth first searching, you will have all of the node that actually you can visit using current mode. Okay, using current mode. So there's another one called transpose of your node. Okay, transpose node is to get your reverse graph. Okay, so you go to your adjacent node, and then you push back a certain node, okay, into the adjacent map. That's the reverse map. Constructing the reverse map, we call it transpose function. Okay, and then you can add a certain edge. So from your source to destination, so your source neighbor will push back the D with it. Okay, so that's the 18 edge to your graph. Okay, and then you have a field order. Field order, you have the source node and then visited node and stack of the stack. So this one you will, if there's a node that you actually try to visit, but you already been visited, then you will push it into the stack. So here, if it's not visited, you will continue to do a field node. Okay, otherwise you will push it into the stack. So this is, so the stack will push in those nodes that you already been visited. So say this one you have a 1, 2, I'm sorry, you have 0, 1, 2, 3, and 3 will visit the 0. So once you visit the 0, you try to visit the 0, you will not visit it because you already been visited. So at that time, your 3 will be first to be pushed into the stack, because this one is step first. Step first, your deeper one will be pushed into. So by doing that, this field order will fill in the vector stack for the node that actually already visited, and then it will be in the depth first order. So this one will eventually fill up your stack in the reverse order. That's the purpose of this field order one. Okay, and once you have that field order one being filled up, then you should be able to do print a strongly connected component. You got your stack, okay, and you have the validity information, okay. You immediately set it to be false, and you actually go through every node for the field order. You fill every order and you do transpose of your graph to create a new graph. That's a reverse graph. That is to create your reverse graph over here. Okay, that's the reverse graph that you actually create it over here. And based on that reverse graph, it pop out, and then it should be able to create your strongly connected component. That is right here. You actually fill out the transport graph, and you set your VDD graph to be empty again. So while the stack is equal for false, it's not empty. Okay, it's not empty. While the stack is not empty, you actually get a node and pop it out. Okay, and then if the node had not been visited, then you do depth first searching. Okay, if already been visited, then that means it's part of the strongly connected component. Okay, that's actually tell you that's a strongly so basically you see our change light at that time. Okay, that actually terminate one strongly connected component. So those strongly connected component will be print out. Let's see where it will print now. Let's see. You call the field order, and then it will need pop out. Okay, that's wrong. Okay. So this CL is when you do it, it will basically change line. So that's search for CL. So CL happen when you do that first searching, it will print out a node. Okay, you print out a node when you actually searching a current node. Once you go into the node will be printed out. So when you do the so-called depth first searching, you have a field order, and your field order right here, you have a field order. So when you have a constructor, you build the whole so-called edges. Okay. So basically, this one is actually print out a strongly connected component based on this VDD, and then compute for the reverse graph, and then finally you actually pop out all the stack, and then if the stack you actually can no longer VDD certain node, you will change line. You will just do change line. Or once your last one, you pop out, and it no longer can be doing traversal. Then you will pop back. So this you're keep doing that. You have 0, 1, 2, 3, 4. You have this one. You go to here and you go to 0, 0 already being VDD, and 3 have no other node. So basically, you pop out each one of them, you will actually get the strongly component up to here. Then you go into this one with the 4. So this one, you go to the 4, but you actually do not create a circle. You do not create a circle because you do not visit something that you actually never visited before. So this is not part of a strongly component. So if it is a strongly component, the reverse graph, we should be able to pop them out back. Okay, that's the fundamental theory behind it. So this one is a example of the strongly reverse strongly component. Okay, and strongly component usually is used to check if you had a transitive relationship. That means that this whole group is something you can visit. There are other groups you can visit. So when you actually have some problem that requires transitive visiting for several groups, you can do that. Okay, you can do that. And you can consider this is the so-called equivalent class. Okay, you can also call this one as an equivalent class. Okay, any questions so far? Hello, any questions so far?
No.
No.
Okay, this is a so-called strongly connected component, okay? Strongly connected component is also one of the things that you will analyze. Shortest path, minimum spanning tree, and strongly connected component. But when you will do what will depend on the graph problems, okay? So right now we are just still covering the basic graph algorithms. At this moment, we are still covering the basic graph algorithms, okay? Now let's go back to this book. So next one, what we will see, actually we talk about this is a ninth tier problem. Okay, so let's look at something else. I'm sorry, let's actually look at, before we go into the next graph, let's actually look at another important topic that's called topological sorting. Topological sorting is also another important graph analysis problem, okay? Again, this one right here is only one segment and no coding, so this is no good, okay? We don't like this one. So let's also do X for X, okay, and say for the T for sort. Okay, topological sorting is another problem. The second problem that we will look at today. Topological sorting takes place in directed graph and return an array of a node where each node appears before all the node is pointing to. So this is called a topological sorting. So we have a graph. So 1 will go to 2, 2 go to 5. Then 2 go to 4, 2 go to 4 go to 5, 1 go to 3, 3 go to 4. So these are the order, okay? So the ordering of the node in the array is called topological sorting, topological ordering. So apparently this one, sometimes you find some paths, is still very useful. Okay, so if you look loaded the order, it will be 1 go to 2, 2 go to 3. I'm sorry. You have 1 go to 2, 2 go to 5, and then you have 2 go to 4, 1 go to 3 as well. Okay, so you will have a topological sorting of 1, 2, 3, 4, 5. But there's an added edge of the 2 to 3 actually is added order. Okay, that means that if you can you move the 3 above 2, maybe. Okay, maybe because 2 and 3, there's no dependency of 2 need to go to 3 or 3 need to go to 2. There's no such thing, but you can add the edge so that everything can be sorted. Okay. But these two actually is in one equivalent class. Same thing right here, actually 4 and 5, because 4 go to 5, so 4 must be 5. 3 go to 4, so 3 are actually 3 must be 4, 4. So these are related. So there's only one edge that's added, this one. But eventually, because you want to have the total order for every node, so you can have the 1, 2, 3, 4, 5. But 3 cannot be behind 4 and 5. So 3 must be equivalent to 2 or actually before 2 or after 2. Okay, so such a kind of the ordering for the node based on the directed graph, we call it topological sorting. Okay, and it's possible that you have a cyclic. So cyclic graph will not have valid topological ordering because you don't know who go for where. So if the graph have a cycle, then it's not cannot be do topologically sorted because you don't have the real order. Is that okay?
Yeah.
And multiple paths allowed. This multiple paths go to one node that is actually allowed, but graph a circle is not allowed. So you must know about you do it actually you must not have the circle. So let's look at the algorithm how it can be done. Okay, so actually you can provide a topological sorting since you have the graph. So basically, your 1, 2, 5, 1, 2, 4, 1, 3. This order already existing. It is a matching of the order so that everything can be sorted. Okay, can be sorted. So basically, you are sorting based on the graph. That's called topological sorting. Okay. So how can we create in the topological sorting using this directed graph? So basically, let's focus on the first node in the topological sorting. So there should be a node you get started from. There is no incoming graph node. So from here, before you do anything, you actually visit it. Since there's no circle, so there should be a node that actually has no incoming data. So based on your so-called adjacent matrix or adjacent list, you should be able to find a node that has no incoming edge. No incoming edge, then that is the node you can do first node. And then based on that first node, you can actually find the order. Okay, you can find the order. So let's assume that you find there's a node, say B is the in degree 0, that actually is no incoming edge. So you can go through the map based on its age. So age node 1, 2, 3, 4, 5, and there are different ages. And based on the age, you say some node, calculating each node's incoming degree, putting them into an array. Okay, that's actually is doable. And then find the one that's actually being 0. That would be the node that you will get started. Okay, that would be a node that you get started. So that's assume that you put the B into the first node, and then there are its neighbors. So its neighbor may be E, maybe C. These will be the node that you will basically go to. But if you take out B's neighbors, and then there's a node that has no incoming edge, that one can be put into the second order there. So based on doing that, you pick one by one that everyone that has the lowest possible incoming degree, you should be able to solve the problem. Is that okay? I had that. Is that okay so far?
Yeah.
Based on you choose those one that has no incoming edge. That's a null, the BE or BC. So then you actually, based on this map, E is the next one has no incoming edge. So you keep track of every node's incoming edge. And then whenever you take out, you actually reduce the number, take out, you reduce the number. You should be able to find who can be put into there. And if there are two nodes that you can get started, you just pick one. You just pick one, okay? and repeat that until you find every node. You should be able to get your, so you push in your E, okay. And then the next one, you take out the H from E, you actually have an A or C, you find out A had no incoming H, instead of C, you put your A there, and then you go C, and then you go D, okay? So this is a topological sorting. So topological sorting will build up the dependency for node of multiple paths. Okay, node of multiple paths. This one, is a Java program. Okay, let me actually try to find a C double plus. So C double plus topological. Let's use a program Z, okay? I trust this website more. So topological sorting is a directed graph, okay, acyclic, no cycle one, okay. And then the topological sorting. There's an in degree calculation, there's a Q initialization, Q in, okay. So the time compressor is order of V plus E plus V plus V plus E. So actually is an order of V plus E algorithm, okay. It's an order of V plus E, the number of vertex plus H. Because each time you need to see how many vertex, and each vertex how many H. Okay, that's the total complexity that you will have. When you find a no incoming H, okay, no incoming H, and you remove one and more than, that's also a degree of that. So, but this one we do not see the code. Let's see, let's actually. So useful guide do have a topological sorting one. There's a problem called right here, but this one, no, this is not good. Let's actually do use the gigs for gigs. So let's see, this one may be okay. The AI result may be okay. Let's actually copy this one. It is a so-called Kant's algorithm, okay? Okay, let's look at this Kant's algorithm. Because this Kant's algorithm has a topological sorting. You have number of vertex, you have a vector or vector T integer. So this one is adjacent list. I'm sorry, adjacent matrix. Okay, adjacent matrix. So based on this adjacent matrix and number of vertex, you actually also initialize the incoming edge, how many incoming edge each one has. So basically, you go to every edge in the map and then mark the incoming degree. So you actually check everyone. If someone go to you, you will increase the incoming edge, okay? And then you actually create a queue, empty queue, and then you check if the incoming degree, you push it in, after you push it in, you will actually remove the edge. You will remove the edge that actually that from that node to other node. Okay. And then you will actually change the size of your incoming edge. Okay, and continue to do that to reduce the incoming edge. And then push in if the incoming edge becomes 0. Any node that has incoming edge, you start to push it into the queue. So by doing that, the queue would have eventually get your all of the node in the topological sorting order. So this one is considered to be a easy algorithm for this Kant's algorithm. Okay, let's run it. Okay, whatever this one is. Okay, so this one is topological sorting. Okay, this one is topological sorting. We go through these different algorithms. Right now, we are not solving the problem. We are actually going to the study of the algorithm. Okay, and this topological sorting is of order of V plus E algorithm. Okay, so basically that's another algorithm in this chapter 9. Okay, so today we cover the solid component topology sorting. Next one, let's look at the so-called nice T. Before we go into the nice T, let's look into another problem that's called King's move. Not night, King's moves problem. Okay. So King's move problem is like when you play chess, you try to find the minimal number of moves the king can go from one node to one location to the other location. Okay, some of the move may not be doable, but you do that first short searching to do it. Okay, but it's not only one pass, because your chess is like this. Okay, your chess is like this, and your king is here. You go to here, you actually can go this way, can go this way, can go this way. But some of them is not a legal move. Some of them is a legal move. So it's not only a shortest path algorithm, you can also be you also need to be based on the rule of the chessboard. Some of the location you cannot do. So this one actually is a robotics problem game design solution. Okay. Okay, so right here, code force has such a problem for King's move. Okay. Input, you will get a E4. So that actually is a E and 4. That's your King's location. And print the integer, that's the number of moves permitted by the king. You will see how many moves you can do. Okay, that's King's move algorithm. So let's see. This solution is, this problem is too easy, okay? Too easy. This one just check for one step, so it's pretty easy. I should just copy it. Let's call it king 0 at CPP. It basically just check the nearby location. If it's not out of bound, if it's actually not out of bound, then you will increase it, okay? Let's check different one. Let's actually do this MOOC problem solution. Let's put this one into in one the CPP. So this one you do use a vectors. Each vector you can have a move. So you are here, you can go a directions. So these are the so-called D0 to D7. Okay, you can go D0 to D7. And then your board is actually VDD. So you reading your source and destination, start and target. You're starting XY and you're targeting XY. Starting from here and here, and then you have the Q or tuple, okay, and you push in Q with save for your steps, save for your step. The Q was save for your step, and you have a ball visited, so you save for which node you already been visited. It's the same as your A by A chess ball. Okay, so while Q is not empty, Q is empty means that you actually pop out everything from your Q. Okay, so you actually go from here to here. You actually go there, and then if it's visible, you actually put it into there. Okay, so you put into your one step into your Q, and then you use that step to go to the next one. Okay. So you keep doing that, If it's legal, and then you go from your source to your destination using the depth first searching, then you should find the solution. Okay, you should be able to find the solution. So let's run this one. So let's do G++ Q1 the CPP -O Q1. And let's run Q1. You enter 22255. So 22255, you need to take 3 steps that actually 22 to 33 to 44 to 55. Okay, that actually is 3 steps. So you do depth first searching to see which will give you the shortest path from your kin to the destination. So kin 0 is single step solution. Kin 1 is actually multiple step solution, okay? But this is another thing that you search your map. So next one we go to the next problem that actually is the nice keyword. So kin, you go 8 directions. Here, 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 here. Now, next one is you look at the night. So your night is different. Your night is going by nice pattern. So let's assume that you start from here. You can go this one, 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 this one. Some of them are legal move. So this one also, you have 8 different possible move. But this 8 different possible move for night is different from the key, but the algorithm should be similar. Is that okay?
Yeah.
Because right now your key's algorithm, you push in the vector of +1, -1, basically for the 8 direction. Now you actually just change the vector. You should be able to finish the nice version. Okay, that's all we need to know. So nice keyword problem is to go from the possible 8 different night location. So it's like just like this, okay? So you just do that first searching with multiple steps. You should be able to find out which one will go from one nice location. So maybe this one, and you go back this one, and then go back to this one. You actually 2 steps, you can go from here to its neighbor here, okay? So that's the algorithm for nice keyword graph. So nice graph and nice keyword also is also a depth first searching algorithm, okay? So let's include all of the code right here. Okay, so right here, let's call it night. So this one, you create a night graph with 8 by 8, okay? And you do breadth-first searching, and you do traversal over it. Okay, so basically this, you have a vertex. Each vertex has its ID and a map connected to its nearby node that you can connect it to. Okay, so vertex, you have the color of the place, and also you have the connected nearby node. Okay, you can add neighbors, and then every time you go breadth-first searching into the different neighbor until you actually find a path from your source to your destination. Okay, so here you have do breadth-first searching to find a node. Okay, that's all you need to know for this algorithm for the time being. Okay, this type of algorithm actually you just know about the purpose, because right now you remember the code, you actually cannot 100% remember all the code. I'm sorry, this one actually, that's actually wrong terminal. and it show you the different step. Okay. Any questions so far?
No.
So this one, I think that at this moment, the algorithm, you can go into the detail to study how this algorithm being constructed. But the basic idea is actually similar to the King's algorithm, King's MOOC. This is a little bit too complicated. Okay, let's actually try different version. This one is from this website. I think it's a little bit too complicated. Let's check this AI version, okay? I think this AI version is easier. It also uses the X move, Y move. I like this version, okay? So let's copy this one to put it into the nice number 2, okay? So nice number 2, you enter the size of chessboard. Let's assume this is 8 by 8, okay? So let's input 8. Then you create a board of the 8 by 8, okay? And then the possible move for knight is like this. And your starting position right now set to 0, 0. You're like that. And then you would have a destination location. Then you recursively doing depth searching to go to the different moves. Then it will go, okay? Then solving the nice problem. Let's go to the solving the nice problem. So solving the nice problem is actually a recursive function. Okay, and you cross each vector. Try the all possible vector. It must be safe inside the board. If it is inside the board, then you actually can add the counter, number of the counter to go to that destination. And then you actually should go to go to a certain node with a shorter number of steps. And if you pop out a certain stage, you will reset that location to be -1. Clean up the node. Okay, clean up the node to make the node available for the next move. So you go one by one until you reach that first destination that actually reach your so-called targeted location. Okay, then you solve the problem. Okay. Okay, so let's actually look at this one. So let's try 8. So this one is show you the step-by-step depth first searching. So let's assume that you get started from here, it jump to here, do one by one, and do depth first searching. You will eventually go through every node in the whole space, 8 by 8 chessboard. Is that okay?
Yeah.
So this nice keyword is going to all of the 64 locations. That's one way. The other one is that this is one purpose for doing nice keyword. There's another possible solution, not for every node, but basically go for point A to point B, just like the King's 1 algorithm. Okay, And usually the keys one algorithm is more useful than this total T1. Total T1 is to visit all of the 64 location in the board. You just do a depth first search and you will basically put a number into your each node. If the node had not been visited, then you will put a number, and -1 means that your node had not been visited. Okay, so this one, the algorithm is not very hard. You just need to know about the depth first algorithm, okay? Okay, so today, basically, we briefly go through the different algorithms in this whole chapter. So let's actually review the whole chapter. First, you need to know about how to construct a graph using the adjacent matrix and list. Then you need to know about the depth first searching and breadth first searching. After that, you look into the Dijkstra algorithm for the shortest path. You go into the so-called Prim's algorithm for the minimum spanning tree, Cruz-Coast algorithm for minimum spanning tree. Then you go into the so-called topological sorting algorithm, also strongly connected component algorithm using the Korasa-Ju algorithm for strongly connected component. Then the nice move and also the kids move algorithm when you do 2D traversal for the chessboard. Okay, and that's about it for this chapter's basic algorithm for graph and for the graph and for the graph. So next one, we are going to go into the so-called user code part to solve the problem. The next one is concept problem. Okay, so here you will have the data structure, dynamic programming, shortest path. These are primarily the graph algorithm. So today we will also look into the flat field algorithm. Okay, look into the flat field algorithm. I try to use a different version. Graph field algorithm in C++. Okay, here we have the code. Let's look at the problem now. So the graph field problem is an algorithm used to determine the property of a area surrounding a particular cell. So you have a cell right here, you have the 4 neighbors. The algorithm is particularly used in bucket field of the paint color. The 2 color, the similar colors pixel with another color. So you fill this one as red, the nearby cannot fill the same color, but you may fill other color, but to make it of different patterns. Okay, so this is a so-called painting problem, coloring problem. Okay, so the algorithm is that you actually pass a target cell of the X and Y value along with a color to be filled in the current cell. It perceives the value. If the XY is outside the screen, it will return. You will not color in it. Otherwise, the color of the XY is not the same with current color, then return. Okay, nothing but recursively calling the function of the 4 neighbors, put in different colors. So that's actually all you need to know. Okay, so let's copy this code and then put it over here. This one called graph field. So basically, you have your color like this, okay, and you start it from 4, and your new color is 3. So you actually find color my screen with new color. okay, and you update your screen. So you get started from 4.4. 4.4 is here. And you fill in a color, so you may fill some color with it, okay? So that's wrong. I'm sorry, this one actually. Let's save all, let's quit it, okay? Let's actually use the terminal. Okay, so you have the updated color. Like that, okay? Anyway, that's actually is a simple algorithm. Let's look at the user code site. Okay, so it actually is a connected field problem, okay? So farmer chunks are broken into fields with paths between some of them. Unfortunately, some fields are not reachable from other fields via paths. So if you are reachable from one neighboring node, we actually would mark the number of the field, okay? So define a super field, a collection of fields that all reachable from each other. So this is a connected component problem. Okay. So you have a field, this one you reachable to these neighbors. You mark this neighbor that you can feel it. So this is problem actually in the user code gold problem, silver to gold, you commonly see this one, okay? So you do depth first searching to go to the connected component, to calculate the component of graph. You start it from one node, doing depth first searching, the all availability node will be its component, and you mark the number 111. So all these is your neighbor. So basically, you go to the different node to start to do depth first searching, and then once you are done, you put in everyone with the same connected component. This is called flat field algorithm. And so right there, in this algorithm, you actually originally have one map, and then you actually use a new number to fill the number. You will actually find all of the connected component in that graph. That's a flat field algorithm. So you can do breadth first searching for it. Depth first searching is also okay, since you are searching for it, okay? Anyway, so again, we are up to here, okay? And next one, we are going into the peso problem. Is that okay?
Yeah.
We start to look into the graph problem in user code, okay? Okay, we finish the basic algorithm part, and so the next one will be more challenging, okay? It's a IOI 94 problem, okay? Okay, see you next time, bye-bye.
Bye, thank you.